Okay, let's get started. So, what'd you think? I heard a collective all right. So that's so I'm gonna try my very, very hardest to get these midterms graded by Friday, and so I'll bring them on Friday, and then of course you can look at them. I can't talk about solutions now because for very good reasons, some people have to take it tomorrow. So I can't talk about solutions yet, but I can definitely, so after they take it, I'll post solutions and then we can talk about it on Friday. Okay? But any questions otherwise about the test? Yeah?
So if we do better on the next exam, that replaces it?
Yeah. Mm-hmm. And if you do better on the final, then the first two, it replaces both of the first two.
So does that mean the next exam will be harder?
Well, it's worth more points. Let's put it that way.
Okay.
And it encompasses more material. So make that of what you will. Yeah. Yeah. Mm-hmm. First two. Yeah. Yeah. So if a later test is better in percentage than the earlier test, it replaces the earlier test with the same percentage, just for that particular test. Yeah. So what I want to do is to emphasize the material from now until the when midterm 2 happens. But of course, you need to know some things like what is a decidable language, because if I say, is a DFA decidable? Then you need to know what decidable actually means. But I'm not going to explicitly ask, are non-deterministic Turing machines equivalent to standard ones? I'm not going to ask something like that. But focused on the later material. But of course, it can include earlier material. Yeah.
If you do worse on midterm 2, you get like both of them.
Worse than midterm 2, and then what's the situation for the final?
I don't know, maybe like it progressively gets worse.
We all hope that doesn't happen, but no, it only goes forwards. No, backwards, I mean, yeah.
So you just keep the old percentages?
What's that?
You just keep the old percentages then?
Yes, yeah. Because it includes this material from midterm 1, so that's why it makes sense to do that. Other general questions like that. Any questions about, another thing. PSET 2 is almost graded. I have to do the extra credit questions, but by tomorrow, PSET 2 should be all graded. The grades are a lot lower than what I expect, so maybe some adjusting will happen, but we'll see what happens. But any questions about PSET 2 or 3? Yeah.
So what format do you want me to do it? Like
I don't know what you mean. Turn what in?
The announcement that said that we were turning in different files and then not putting our name on it.
Yeah. Mm-hmm. So just like if you happen to include multiple PDFs for whatever reason, make sure your name and ID are in it so that it's easier to link it on Blackboard. But we prefer that you have it in one big PDF instead of multiple PDFs, but if you happen to have multiple ones, then just have your name on each one to make it easier for the grader. Yeah. Yeah, so it's an English interpretation of what I want it to mean formally. So specification is described by a DFA. So we have this DFA S, which is S is a DFA, is the specification. And we have this other machine that we're given, and we want to check whether it satisfies the specification. It's that one, right? Yep. So basically, anything, so if you can think of this as the language of S, like all the strings that the specification says are okay, then included within here is the language of the DFA that you're given. But, so this is what we want to happen. do we want, say, this to happen? I made it in red for a reason. No, why not? because it's in red. Why not? Right, there are some strings out here that don't conform to the specification. So what's a different way of phrasing checking whether this is the actual condition? Whether D's language, whatever D does, S also does. What's another way to say that? The language of D is a subset of the language of S. And so going off of that, what about the second part? It says like completely abiding or something, some made up phrase I came up with. What is that actually saying? Yeah, they're exactly the same. So this is part A, this is part B. And what we want to check is whether they're the same or not for DFAs. Is the equivalence problem for TMs decidable? No. So what I'm showing here is that it actually is decidable for DFAs. So in fact, there is a difference in the model. So the reason why I'm giving these questions is to show you that there is a difference between these computational models. Okay, does that answer your question? Good. Other questions about P set 2 or 3? I didn't hear that.
Why did you get rid of it?
Because if like your boss or something doesn't know the theory stuff and proposes this to you, you have to think, how can I phrase this in a formal way so that I know to apply the techniques that we do in this class? But because they're going to write something completely bogus to you, right? So you need to be able to interpret that. So I'm doing a research project where a lot of the terms are not formal at all. And so my task is to actually make it formal. So I have to interpret what they say and propose a model for it. So I'm actually doing a similar type thing in this class. So it really actually does happen. So it's not just like a made up thing. Any other questions about P set 2 or 3? Okay, so what were we talking about at the end of Monday's lecture? Well, we talked about these DFA things, and then we proposed this problem about concatenation and star, and we didn't really see how to do it for DFAs. And then we talked about, instead of DFAs, NFAs, which help solve this problem in a much easier way because we can have these Epsilon transitions between various states, and then we can just glue various NFAs together. And the really interesting thing we saw at the very end of the lecture was that DFAs and NFAs, do they have the same set of languages, the regular languages? Yeah, and what was the idea behind that? Yeah, we converted an NFA to a DFA, but what is that, and what are we trying to do with the DFA? Well, remember we were talking about subsets of states of the NFA, and then in the DFA, we link these subsets together based on what the NFA's transition function tells us to do. And then we incorporated the epsilon transitions in there by talking about this epsilon closure thing. Any questions about that? So I actually, I'm not going to discuss the solution to this, but recall this problem from the midterm. That's not a good squiggly. 0, 1, the DFA question. So W, I think, starts with 1, 0 and ends with 2. So is this very precise? No, why not? Although it's kind of precise here, meaning what starts with means, that's kind of unambiguous. But you notice that several times throughout the class we've had this issue about what does this English description of this language really mean? Do I include the empty string or not? Do I include this string or not? And that's kind of a problem, right? we kind of address this with machines by defining them in a formal way, by giving them this formal definition of computation, but we didn't do the same thing for languages. And so that might make you a little antsy to think, is there a formal representation of a language? And in fact, there is for the regular languages. And so many of you have probably heard or used this before, but we're going to talk about something called a regular expression. Who's heard of a regular expression? So this is actually the third use of the word regular out of 4 that we'll have. If you see regular expression, like parser or something, or generator, it's actually not necessarily the same thing as this, because some regular expression parsers can actually recognize non-regular languages. So what we're going to do is have these recognize the same languages as the regular languages. So follow this convention and not necessarily some other convention, because it might give you more power than what the regular languages have. So the way that we're going to define this is, instead of talking about a machine model where we test a string to make sure that it accepts or not, what we're going to do here is we're going to describe the regular language. And the way that we're going to do it is we're going to have the regular expression, as you might expect, be a string, and it describes a language. And so what we're going to do is we're going to define it in an inductive way. So we're going to have some base cases for which these are regular expressions, and then we can inductively combine these to form larger regular expressions using some operators. So we're going to say R is a regex if and only if one of the following holds. So we're going to assume that sigma is an alphabet that we can work over. So just like a DFA or NFA or whatever. So the first definition is if R is the empty set. So if I write empty set down for you, is that a regex? Well, according to this definition, it is a regex. So if I just write down here empty set like that, that is a regular expression. Okay? It's not a very useful one, but it definitely is one. Another one that we want to have is, so the main reason behind this first one is we want to capture the regular languages. Is the empty set language regular? Yeah, we can just have a state that just loops on everything and is not final. And so therefore it doesn't accept anything. So we've got to have that case in there to capture that particular regular language. What's another regular language that seems kind of on the borderline like this that we may want to accept? Well, sigma star, but we'll actually handle that via the inductive cases. What about another small language, not empty set, but a small language like that? Well, how about just the empty string and no other string, right? So can I have an NFA that just accepts the empty string and nothing else? Yeah, so how can I do that? Someone tell me. Yeah, how about a start state that's final and no transitions? Is that allowed in an NFA, no transitions? Yeah, it doesn't have to have all the transitions. Is this a valid DFA? I mean, technically it is, but in what we will use it for, no, it's not a valid DFA because it doesn't have the transitions. Okay, so we will want to have that case as well. So if I write down empty string as I just write that down, that is a regular expression too. What's another small language that's not one of those first two? Well, how about just a single character? Right, if I have a single character, can I, for example, have an NFA for just that single character string and no other string? Yeah, how do I do it? So let's suppose that the character is A. So how can I make an NFA that just accepts A and nothing else? Well, how about this? So I just have a start state, transition on A to a final state, and no other transitions at all. Cool. Well, let's see. So if I have some character in the alphabet, R equals A. So if I write down a single character, that's also a regular expression. Okay, so these first three are the base cases. And then the next three are the inductive cases. So meaning, if I have two regular expressions and I combine them in the following three ways, the result is also a regular expression. So let's see. Are there three operations that we recently just talked about for regular languages? Well, what are they called? The regular operations. What are those three operations? Union, concatenation, and star. So if we apply any one of those three operations to one or two regular expressions, I get a regular expression back. So if R1, R2 are regex, then R equals R1 union R2 is regex as well. Same thing for concatenation. And then this, exactly the same, but for R1 star. So if I do union of two regular expressions, if I do concatenation of two regular expression or the star of one regular expression, I get a regular expression back. So as an example, is this a regular expression? Let's see. Yeah, so why is that? Well, the base cases, I have all of them covered because each one is either the empty set, the empty string, or a single character from the alphabet, and that's fine. And then we can inductively build them up with union, with star as well, union. What about this one right here? A concatenation, right? So sometimes we may need to put parentheses to help us figure out what kind of operation to do first. Should I do the ones inside the parentheses or not? So if I, for example, remove those parentheses, do I have the same regular expression I did before? No, so what string would the previous one describe that this one doesn't? So I'll put them back. How about AAB? Could the one without parentheses describe that? No, because I don't have the star on the A anymore. So I can only choose one A if I wanted to, instead of two A's like here. Okay, so sometimes you do need parentheses to denote which operation to do. Okay, well, let's see. Yeah.
Is that left character no star?
Yeah, empty set star. It's a string, but it describes a language. So, like for example, the language of this one would be the language of A union empty set star concatenated. The language of B union the language empty set star. So it's an actual character this time. It's not in the alphabet, but it's an actual character. So the characters we're allowed to use as single characters are in this alphabet sigma, but we are allowed these two special characters, empty string and empty set, to handle the other two cases.
Does the star do anything on the empty set?
No. but the language would be union empty set.
Okay.
It actually wouldn't change anything, but it's just an example regular expression. Other questions? So what we claim here is that, well, it seems like just by glancing at this, we actually do get the regular languages out of this, meaning that if I have a regular language in mind, there's a regex for it, and the other way around. So why would we think that that's true? Well, let's see. If I can convince you that I can convert from a regex to a DFA and back, would the regexes describe the regular languages? If I found some procedure to convert a regex to a DFA and the other way around, yeah. So therefore, they would describe the same set of languages. Would you allow me to do that with an NFA instead of a DFA? I ask your permission.
Sure.
Yeah, sure. Because why? Why am I allowed to do that? Yeah, because we already showed NFAs and DFAs both describe the regular languages. So if I can convert a regex to an NFA, and from an NFA to a regex, therefore they describe the same languages. So we're good there. So that's what we claim, but we're going to do one direction, not the band, but one direction of the proof now. Let's see. The joke made me lose my train of thought. Okay, let's see. So remember, we have to show that we can convert a regex to an NFA and NFA to a regex. So, so the easier direction is to show that every regex can be converted to an NFA. So in other words, the language of any regex is regular. And then we'll show the other way maybe next time if we don't have time today. Okay, well, let's see. How would I even do that? So if I give you an arbitrary regex R, let's say, and I tell you, produce for me a NFA for it. So how would you actually do that? Well, if I can convince you that I can make an NFA for each of the 6 cases in the definition, is that all I need? Yeah, because every regex is described by applying these cases, either inductively or a base case. So if I tell you the procedure of how to work with each of these cases, then we're done. Okay. Wait, didn't we just do the first 3 cases? Great. So let's move this down. Okay, it won't let me. All right, well, let's see. For R equal, I'll just redraw them. For R equals empty set, we already made that. I made an NFA that just had one state not accepting no transitions. So that's easy enough. Empty string, that's easy enough as well, almost exactly the same. And R is a single character. Well, it's a little more non-trivial, but we can accomplish that with a 2-state NFA, just by reading an A and having no other transitions. So the good thing about NFAs is that I can just forget about any other transition I might need, right? I just only focus on the one, any other unnecessary transitions. I only focus on the ones that I actually need here. Any questions on the first 3? Well, let's see. Well, we have 2 more to go. So I'm assuming by induction that I have an NFA for R1 and an NFA for R2. Is there a way that I can get union easily for NFAs? Well, let's see. Could I use Epsilon transitions to help me? So let's suppose that I have an NFA for R1 up here and has some start state, and an NFA for R2 up here, down here. Could I get an NFA for the union of those 2? Yeah, so how would I do that? Well, how about I have a start state that epsilon transitions to both of the start states? So new color, epsilon, epsilon. Does this actually get the union? So don't think I'm not selling you swampland in Florida or something weird like that. Don't think about it. Am I actually getting the union here? Well, think about it. What does non-determinism mean? It means if there is a way to accept, it'll pick the right path. Well, let's see. If R1 says we'll eventually say yes for it, will it pick the top path? Yeah. Well, or it could pick the bottom path, but that means that the other NFA will accept it too. So that means if at least one of them will accept it, I will pick a right path and I will accept. So that means I do get the union here. Cool. So that's actually really easy. What about for concatenation? Oh, wait, didn't we do this on Monday? Yeah, we actually did this on Monday, remember? So we had, so I'll just call it R1, even though it's an NFA, just to make it easy. So if we have, so if I have R1 over here and R2 over here, how do I combine them for concatenation? Just as was suggested, I make the first one's final states no longer final because I have to get through the second machine, but I epsilon transition my way over, like that. Cool. So that's actually really easy. What about star? So if I have an NFA for R1, so what do I do with this NFA for R1 to have it be the star? Well, I gotta add this new start state, right? And why do I have to add the new start state? Exactly, I have to accept the empty string. The original NFA might accept the empty string, but I'm not making any assumptions about it. So, but I gotta do that. And I wanna start at the original start state without having read anything, so I have to epsilon my way in. But what else did we have to do? Epsilon from the original final states to this, either the old start state or the new start state. I prefer the new start state. Wow, so this is actually really easy. I can convert regex to an NFA very easily. So we'll do an example, but are there any questions about that? Okay, let's do an example. So again, now I have to think one up. So let's see. Okay, that's complex enough. So we won't deal with empty string or empty set or whatever. So, okay, we'll deal with that when we get there. So what are the simplest building blocks of this NFA? Sorry, of this regex. The character A and the character B. So what we're going to do is we're going to start from the bottom and build our way up until I get the full regex. So we're going to start with the base cases. So if we just look back at our construction of the NFA, we know exactly what to do for each of these. So I'm not going to connect these in any special way. I'm just going to apply the constructions above like a machine would. So I'm not thinking, well, okay, if I see a B here, I'm going to immediately put an A after it. I'm just going to apply the construction exactly as it describes to do. But I know how to do A a single A and a single B. Okay, so we got the single characters down. What about what's the next level up above that? Well, can I do the union now? No, because I have to handle the BA thing first. So I'm just gonna mark these so that we can keep everything straight. So BA. So I'm gonna do something here and it's not right, and I want you to tell me why it's not right. So what you might be tempted to do is this. Oops. So this NFA definitely has the language BA. That's without question. Why is this not a good idea? So think of this as a concatenation of two regular expressions and not two characters. So if we think of it that way, if we look back to concatenation, we gotta take the two NFAs for both of them and then have an epsilon transition from the final states of the first to the start state of the second. Well, do I have an epsilon transition from the original final state of the first to the start state of the second? No, there's no epsilon transition at all. So this is definitely not the right thing to do. So what we're going to do instead is I'm going to copy and paste my two NFAs that I actually need. So I'm just going to straight copy them. And the construction tells us that you make all the final states of the first no longer final, and you epsilon your way over from those to the start state of the second. So you may think, well, okay, that's pretty stupid, right? You could definitely make a smaller NFA that does exactly the same thing. And so therefore, when you make the NFA at the very end, you will have a much smaller NFA and your coworkers will like you, you'll get a big bonus, life will be great. Why should I do it the second way, not the first? It's guaranteed to work, first of all, but even more importantly, could a computer do this? For the BA, for the first example, I had to think, oh, I can just glue these together. Do you think a computer can figure that out in the general case? Not necessarily, but this is guaranteed to work. Okay, does that make sense? So the entire purpose of that is to make this process algorithmic, and so that a computer can carry out the simulation. Okay, so we handled the concatenation, fine. What's the next level up? The union. So let's handle that. A union BA. So now I'm just going to copy and paste the NFAs that I actually need. So I'm going to copy and paste my little NFA for just an A and the bigger one for BA. So I'm going to do union and star in the same example just to save time and space. But in general, you should keep copying and pasting these. Okay, so how do I do the union of these two NFAs again? Right, I add a new start state, and what do I do with this new start state? Yeah, epsilon my way over to the other two NFAs. Yep, super easy. And so that's what we did. So I'll actually put this color-coded. And now I'm just going to handle star in the same diagram to make it easy. So how do we handle star? At a new start state that is final. Good. Sweet. And what does this start state do? Epsilons our way over to the original start state. And what else do I do? Epsilon transitions back from the original final states to this state. Or to the original start state, it actually doesn't matter in this case. Okay, well, did we just make an NFA for the exact same language as this regex? So in fact, we can convert any regex to an NFA. Sweet. Now what about the other direction? So I tell you an NFA now, a DFA, it actually doesn't matter here. If I tell you a DFA or an NFA, and now I got to convert it to a regex. Question for you. Is the NFA going to be of this form? This nice form where we can just parse out what the regular expression is? Nope, it might be completely different. It might not have epsilon transitions at all. It might have something completely different. It might have, as an example, other transitions that do what we don't want it to do. So in fact, we might be working with an arbitrary NFA here. So that actually presents us a problem. So let's try to think about this a little bit. So if we want to convert an NFA to a regex, well, let's see. So let's just think about, well, there may be other states over here and over here, but let's just suppose that we have some state and it has a single transition to maybe some final state that does other things. So just focus on these two states and no other transitions at all or any other states. Do we know the language of the little NFA we have here if you just delete the other transitions? Yeah, we can definitely parse that out. Well, let's see. Let's make it a little bit more complex. Well, let's say we have a state right here, another transition out, and some other other transitions. And suppose we have a loop with some character on it. Do I know the language of this mini NFA here? Well, what is a regex that describes the strings that take me from that first state over to that final state? A, C, star, B, right? So there's like a loop in the middle, and whatever we read going from the first state to the looping state, then C star to indicate we can go around this loop as many times as we want, seeing a C every time. And then we read a B to go to the final state. Good. So we made it a little harder. What do you think I'm going to do next? Make it a little harder still. So let's see. What if we had another transition immediately there on D? What is the language of this NFA now? Yeah, A, C star, B, union D. Because we can either take the top path or the bottom path. Okay? Well, let's see. What if we can just eliminate that state? And we can replace this entire transition with A, C star, B, union D, and of course get rid of this one. Can we do that with an NFA? No, because I can only have at most one character in every transition. So in fact, we are going to need to have a generalized version that allows regexes on here, on the transitions. But suppose we just kept eliminating states in this way, and we whittled it all the way down to a single generalized, as we'll call it, NFA, that has some regular expression on its transition. And it's from a start state to a single final state, no other transitions, no other states, but it's just that a regular expression R. What is the language of that NFA? Just that the language of that regular expression. So if we can take an arbitrary NFA, look at the states within it, and then just rip them out, as it's called, precise term there, rip them out. And if we can whittle it down all the way to two states, then we could just parse out that regular expression on that transition, and now we know the regular expression. But could NFAs have more than one final state? Yeah, certainly. And this suggests that, well, I can't get rid of a final state, because if I end in one of the final states and I want to remove it, then I might be deleting strings from the language. And that's definitely not allowed. But here's a question. Can I convert any NFA into an NFA with exactly one final state? So let's suppose, so that's actually what we're going to show. Every NFA can be converted into one with exactly one final state. Anyone know how you can actually show that? Exactly, precisely. So if we have some NFA with a whole bunch of final states, the suggestion was to make a single new final state, make all the old final states no longer final, and epsilon transition over. So in fact, if I have 355 final states, I can have all of them epsilon their way over to a single final state. So if I end a computation in one of the old final states, I can get another computation, accepting one, that adds the epsilon transition at the very end. And so therefore, we accept those strings as well. Question, what if the NFA had no final states? Would this still work? Well, let's see. What if we had, for example, this NFA that has no final states? What does this procedure say to do? It says to make a new final state, and for every old final state in the first one, add an epsilon transition. How many were there in the original one? None. So am I done? Yeah, every single final state in the original NFA has an epsilon transition over. So in fact, this works for any NFA. Any NFA can be converted into one with exactly one final state. So there's absolutely no possibility of me talking about generalized NFAs in 1 minute and 6 seconds, so I'll let you go 1 minute and 6 seconds early. So we'll talk about GNFAs as they're called next time. Office hours, pretty soon.